Welcome back to lecture 18 of the course Electrical Systems in Agricultural and Biosystems Engineering. The topic is still on uh, electrical controls, and the last time was about PLCs or programmable logic controllers. And in this session, we will zoom in on the very special kind of PLC, or well, others would classify it as a different category of uh, control, but in the sense of function and design, the microcontroller, which is as shown on the screen, is actually a type of PLC. Now let's proceed. What is this that we're talking about, the microcontroller? Let's see the architecture, because that would really be a way to show that this is a kind of a programmable logic controller. Now, shown as a screen is the generic architecture for microcontrollers, and the very basic components are the CPU, input and output ports, actually, and then you have your memory, and these are going out. Okay, although you have your other buses, which are actually the serial buses. Okay, and then you have your address bus, which is just one directional. Okay, one direction. So bidirectional are the other buses, and they're connected to both the CPU, the input and output, and likewise the memory. The input and output, they could be as analog or digital, and then there's the conversion of this analog, okay, to digital and vice versa. Now there are also there's also the memory from the RAM, okay, the ROM, okay, random access memory. You have also your flash memory, the EEPROM, which is a type of ROM, and then the CPU is connected to external devices which are controlling its processing. Okay, these external devices are likewise connected to inputs and outputs. So this is the generic architecture, and we'll try to see how this looks in actual design. Okay, let's move to the other camera to show this electronic device. Okay, so this is a type of a microcontroller, okay, the very first of its kind. No, this is actually a different generation already. Okay, so it's a board, and it has the different components, okay, from the CPU, okay, to the memory, okay, and then you have also the different input and output ports. So from you have your digital ports, inputs over here, and then you have your analog over here, analog ports, and then you have your power source, and you have the main power source for connection to the USB, and this is the alternate power source. Okay. Now there's an oscillator here, this side, okay, over here. It controls the power input into your, or the signal, okay, the frequency signal to your as power, okay, inside these chip. Now it would be best actually to see this in action, but it would take a long time to really work this out. and there's an option out there. Okay, and later it will be shown how to make use of this just with a simulation software online. Okay, particular for those who have yet to have this kind of equipment, okay, or electronic device. So this is an Arduino uh, board or microcontroller, and it's a type of microcontroller applying such kind of the generic architecture that was shown a while ago. Now let's try to compare the the microcontroller, okay, to a PC, okay, the generic design of a computer, okay. So a computer has a CPU, or central processing unit, and it has buses and controllers. Those are connecting. Actually, the buses and controllers are wires, okay, and they are wired to output the display, okay, in the monitor, the sound, okay, the audio, and other controllers. Now, you have also your input, and it's bidirectional, meaning there's uh, it's going back and forth. And then you have also your input and output, which I mean, this is only output. Okay, so I think the arrow should be corrected. Let me try to do that. So I've corrected that, and it shows actually what is happening. The 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 computer, okay, is sending signals to the output, while the input is sending in the signals. You have also your flash memory. It's connected to the CPU via um, right now it's the SATA port, SATA cable, SATA port. Okay, and it would, okay, due to advancements in technology, the connectivity differs. There was a point in time when the USB was still in development. I think it was the early 2000s, and previously the USB was unknown. It was generally unknown to the public, and it was only right now, okay, because the USB could deliver power and signal at the same time, so, or in a different kinds of signals. So it has had a massive expansion in the last few years. In fact, it's the standard uh, right now. Actually, a USB, I think it stands for Universal Serial Bus. Um, let me check that, but I think it's the right term. Now, why are we talking this in passing? Okay, because these are very important in the development of control systems in agricultural and biosystems engineering, and the student, okay, an engineer should be able to understand the very basic, okay, because this actually is just a week of discussion on electrical controls, and this is one lecture, particular on microcontrollers. But it gives, okay, the very broadest idea of how things operate, and it would give the student a starting point to further the study, okay, the personal study on this kind of technology. Now, before we go to the details of developing control systems in using microcontrollers, let's try to um, see an example of, okay, of the board I just showed a while ago in the online uh, via online. So this is a sorry, let me just servo movement. Let's just rename this one. Okay, so this is a servo, and you have here a potentiometer. Now, a servo is a type of motor with discretized or identified angular motion. Okay, so this is a potentiometer on the other hand, and if we try to simulate this design, okay, when you simulate, the system is going to run as if it is an actual device. Okay, so this is the very basic of simulation. You try to work out a design before it is translated to reality. So you see that the potentiometer has graduation of levels, and it's graduated, or it has values. And then if you increase the potentiometer value, you could see that the servo motor is increasing its angular rotation. Okay, we know about motors as a, a device that generates rotational motion. So this potentiometer, increasing or decreasing that value, okay, actually a potentiometer is a voltage divider. It has three terminals, and it divides the voltage so that, okay, it's actually a resistor. Okay, it divides the voltage depending on the value. It's a variable resistor, so it divides and we know that the resistor is actually a voltage divider, and then so it it divides the voltage uh, fairly continuously depending on the value. Okay, now the connections. The potentiometer is connected to a power source in the ground, similar to this servo motor. Okay, this is connected to the 5. Okay, you can see the it's connected to the 5-volt power source, and to the ground. It's uh, ground and power. Now, signal is sent out to the digital port, and similarly, the wiper is sent out to the analog port. A basic understanding of this system is that it actually has code in it, and learning the code is a different field in itself, and would require additional effort to learn. So in this lecture, we know that there is a code, and it follows the same. It actually is based on the programming language C++, and same way. Okay, programming languages, particularly object-oriented languages, are set up. So you have your variables, and then your uh, functions, and you have your similar looking. These are conditional statements. Okay, the for do loop. Now, learning this is set aside to, or set in the course programming engineering, or engineering programming, and thus this will hopefully be discussed there. In the context of the class, some code will be given, but not much more on the actual coding itself. All right, the code is given, and it will be provided in um, the handout. Now, let's go to another example. Okay. Now, the program actually is embedded in this microprocessor. Okay. So let's proceed to another example. This is another example, and it shows this is a motor. It actually rotates with an electrical input. Now, this is a LED, this is a resistor, okay, and this is a ambient light sensor. So this is senses light, and this is the usual board that we have. So what we will do is we will wire this so that when there is light, okay, the motor is going to run. Now, again, the code has already been embedded, and it's a very simple code, but okay, we will have the wiring of this, uh, the actual wiring for this setup. Okay, let's try to do it, and let's just um, try to work this out. It should go here. Similarly, this should go to your okay. I'm just running this it's just, I mean, it's very quick. Okay, so hopefully, okay, this will be able to um, make this work. What we see here is that we have the uh, light sensor. Okay, it senses light connected to the power source, and you have your analog signal, okay, going in. Now that is being processed by the code so that it outputs a digital signal to the LED. Okay, that is the resistor is set to 220 ohms and kilo ohms, ohms, just ohms. So this then that's the, well, the LED is just there to signal that there's a power, a electricity coming in, there's current coming in, and then we have um, the a motor connected in parallel to the setup. Let's try to run this and see if it works. So we will, okay, so there's a mistake. There's a mistake to the um, uh, setup, and let's see what could be wrong. Okay. Did I do it correctly? Oh, sorry. I think I connected this wrongly. Okay. All right. Let's correct this one. It should be going here. All right. So it's not running, right? You can see that there's a simulation time. So the temporal setting has been set and is in motion. Now, what we can do, okay, we can actually control the light, okay, and see that all right, what is wrong? Huh, be wrong here. So it's running. Mm, all right, let's just revise this one. So I think I found out the reason. So actually, it's the ground um, terminal. I thought it should be coming in, no? But the programming does all um, the work here. So let's try to change this, okay, and set up the ground. Similarly, this should be connected to the ground, while this connected to a power to a signal. And hopefully this is going to already work. Oh, it's not yet working. Let me just see again what's happening. Should be probably one signal away. Yeah, so see the difference. Um, and it's working, right? Depending on the signal. Okay. Uh-huh. Could be still wrong here. Let me just correct this one. Mm-hmm. Something's still wrong. I know now. It's the, I think the resistor, it should be ohms. Why is the variable? Something's wrong with this design. Let me just work this out. Okay, work it out. And uh, yeah, so this, yeah, that's part actually of the design process. Okay, so the the photo, that light sensor should be connected. Okay, its emitter should be connected to the power source. So the power source flows from here, and once it detects the light, it uh, puts in a signal to the analog portion. My mistake for saying it should be to the ground. Now the ground should be connected to the uh, or the ground on the digital port should be connected to the LED and the motor. Well, that LED is just there to indicate that there is electricity, and you could also see the rotation of uh, the motor. Okay, okay, because there's only one. What we have here is if it's below, okay, if there's light, if it's zero, then there's no light, there's no rotation. Okay, but if there is, okay, actually the code would say that a value is actually 700. So okay, it depends on the your limit, and that would allow the flow of the electricity to the motor and light so that they are both powered. Now let's proceed to um, the design process, okay, which was what I've shown a while ago. Now, this is a very simple implementation of a control system, and there are very much more complicated, such as monitoring of temperature, relative humidity, um, others, so that they could be used as data. Okay. As to the take-in of data, they could be changed depending on the temporal side of things. Could be a minute, every second. Okay, so let's try to see what are the steps in microcontroller design and development. Right, the first step is to first design. Okay, the first step is to design or define the objectives of the design requirements. What are the needed operational, or what are the operational requirements of the design? And as after that, okay, if it's, for example, in the previous one, it's the operation of a motor with depending on the light availability. Okay, so it could detect ambient light. So the parameters on number two, okay, identify parameters and variables. It's the light, and then you have your motion. Okay, what is the speed a limit, or a the threshold? Okay, and then you have your number three, understand the sensors that are needed. So you have to have their a motor, an electric motor, and then a light sensor, ambient light sensor. Others could be others have very much complicated designs, okay, so that you would need actuators. And then you select the appropriate microcontroller. So seemingly our use of an Arduino board is enough. And then you design, program, and simulate the control system. So that's the coding part. And then simulation, as we have just shown. And then you deploy, okay, well, first building it, and then deploying it and debugging, which I've just shown a while ago in the background. You debug the prototype of the control system, and you document the system. You could add another step, and it's the manufacturing of the system in large quantities. Okay, and in that case, you would no longer be using the microcontroller off the market or commercially available, but redesigning or retrofitting it to what you just need. Okay, because you see that this this board actually has a lot of uh, extra unneeded components in the actual implementation of a specific control system if it's going to be mass produced. Okay, so in the next discussion, we will talk about motors, and that has just been electric motors, and that just has been discussed or included in the discussion a while ago with the servo motor and the electric motor, the basic electrical motor. Well, these are DC motors, but and in the next discussion, there's, well, AC motors as well. I'll see you and thank you for listening.